energy, right? The system tends towards a lower energy state. And here's mechanical equilibrium, right? So this umbrella is standing up, and its potential energy is related to the center of mass. And you would not argue that this is the lower energy state. Okay? But in order for this umbrella to come from this state to this state, there has to be what's called activation energy. We talked about it. What is that activation energy is equal to? The center of mass has to be raised a little bit when we do this rotation. So from here, it goes to here, and this activation energy is very small. But the gain in overall energy is large because we have this height, and then all of a sudden we have this height. So this is energy is proportional to that height, right? So we gain this much by spending that much. And most of the materials are stuck in the metastable states, like the chairs that are made from plastic and made from metal. There's a lower energy state when it is oxidized. And that's what we're fighting here. We're fighting with nature. We're wanting to prevent the nature from causing corrosion. There's a reason why this corrosion happens. How can that be prevented? Well, we already learned that corrosion consists of two reactions, oxidation and reduction. And this happens in the presence of some sort of a liquid, a solution, right? So if we somehow provide a barrier on the surface, in this case of a metal, then the species are not going to react with that metal. And that's called passivation film. If you look at this aluminum has a native oxide layer of about 100 nanometers. It's naturally occurring. But how many of you have an aluminum boat? What are most of the boats in Florida made from? Have you ever been on a boat? Fiberglass. Why? Well, you can make an aluminum boat that's going to be much more efficient for the weight and cheaper than fiberglass. In fact, I have a friend who is working for a company that does design and inspection of drawbridges. He's a mechanical engineer. He has an aluminum boat that he had imported, and it cost him $15,000 just for the shell of that boat. And he can tow that boat with his Mazda Protege. Can you imagine? So if you have a boat that's made from fiberglass, a decent boat would start, have you been to the boat show? Like, a decent boat, how much would that cost, do you know? Any idea? Like Grady White? Anybody knows Grady White? Nobody knows Grady White? You don't have rich friends with a boat? Well, let me tell you about the boat. There are a couple of jokes. One is that a person who has a boat is happy 2 days of his life or her life. It's when they bought the boat and when they sold it. It's expensive luxury stuff. So a decent boat, $200,000, $250,000 new. You can buy a used boat. Does anybody own a boat? No? Who wants to have a boat? Okay. This Grady White, if my friends bought this boat from 1995, and they paid whooping $10,000 for it. So the value and the price just plummets down. Going back to the aluminum and to the performance. The reason why it's not a very smart thing to have an aluminum boat is because aluminum corrodes in the salt environment. So if you're using the boat in the fresh water, it's okay. If you're using it in salt water, it's going to corrode, and this nice native oxide that's 100 nanometers turns into white powder. How many of you have seen corroded aluminum? You know what I'm talking about? You don't know? You've never seen it? Okay, another way. We, in this class, always talk about temperature, how hot things are. Why? Because there's exponential dependence on temperature. In fact, increasing the temperature by 10 degrees doubles the reaction rate, whatever that reaction is, chemical reaction, interfacial reaction, oxidation. Okay, and another way is to apply a physical barrier. So painted or coated, like you can see, there are a lot of surfaces here that were painted. Look at this. See that strip over there? That's unpainted concrete. Why is it there? Because there was some sort of a conduit, you see, and then that got relocated to the left, so that area is not painted. Another way is to put an inhibitor. It's added to the solution to decrease reactivity. And I can tell you that the biggest business in Florida that comes from mechanical engineering and civil engineering, which is not affected by the economy whatsoever, do you know what that industry is? HVAC, air conditioning, and refrigeration. Because when it's hot, you have to fix the air conditioning. And the businesses cannot operate if there's no air conditioning. The reason I was asked to teach the second class, Materials 2, Material Selection, Mechanical Design, is because students in mechanical engineering were selecting the materials like mild steel for the housing of an AC system. How much do you think is the price of an average air conditioning system for like a house or an apartment? You have any idea? How many of you have a portable AC that you stick in the window? Anybody? No? You do? How much is that, or was that? You don't know?
I don't remember, but
Huh?
I don't remember, but I remember it was a lot.
Okay. It's in the thousands of dollars, so it's an expensive item, and it requires professional installation. So once you install that system, you don't want the housing of the air conditioning system that was installed to rust. Yet, the housing of the air conditioning system, people say it's not critical, so it's painted. And in 5-10 years, it starts to rust. And while the AC system still works fine, all this rust around doesn't look aesthetic, and the system needs to be replaced. And that's why you see those air conditioning systems that kind of fail. Okay, so what do those inhibitors do? They slow oxidation and reduction reactions by removing the reactants. Like oxygen oxygen can be retarded by this inhibitor. There are different types of air conditioning systems. Have you ever heard about a geothermal system? It's very popular. How about evaporative cooling? Have you heard about evaporative cooling? Okay, when was the last time you went on the beach or swimming in the pool? Anybody? Ever in your life, last time? Okay, I want you to remember what happened when you got out of the pool or out of the water. What was the first thing normally people do when they get out of the water? Dry themselves. How? With a towel. Why? It's cold. Why is it cold? Water, even in the summer when the water is body temperature, okay, I want you to picture this. You are sitting by the pool in your swimsuit. Okay? Do you feel cold? Okay, and then you get into the water and you get out. You compare your sense of temperature before you got into the water and after you got into the water. Can you visualize that? Imagine? Okay, when are you cold? Why? Change in temperature. And that's not the reason, but it's a good shot. I want you to think, guys. I mean, you're all engineers. I want you to think about it, because this is going to answer a very interesting question of how this heat exchange works. And I'm not in the business of teaching you HVAC, but might as well touch upon it. When liquid evaporates, in this case water, this is the cooling process. Because when the molecules of water are evaporating, they are taking away the energy, and that's why you feel cold. So in the states like Arizona, they have evaporative coolers. You might have seen them. All it is just a big coil, and the water drips down. And also, if you're ever in Arizona or in California, the pool temperature is way too hot, and people have like a little fountain. Have you ever seen anything like this? What does it do, a fountain in the pool? It cools the water in the pool by evaporation. So there is a process called evaporative cooling. In fact, every air conditioning system that you have is using evaporative cooling. What is inside of most of those ACs? Evaporative coil. Okay, but what's inside that coil? What is circulating and turning into gas and cooling? Refrigerant. Okay, what's another name for that refrigerant? Freon. Okay, so, and have you heard about Carnot cycle? You taken thermodynamics yet? Not yet? Okay, you will, and they will teach you all that good stuff. But this great company called Motorola wanted to work and worked in research and development on what's called a semiconductor air conditioner. And it's a semiconductor device called Peltier stage. And when you apply voltage to it, one side gets hot and the other side gets cold. Where's that wafer? Okay, so imagine that you have a picture on your wall with a frame that you plug in to the outlet, and that's your air conditioning. Can you imagine that? Not complicated as such, but scaled up to a large, maybe the size of that board. And one side is going to get warm, and the other side is going to get cold. And you can reverse the voltage, and then the sides would switch. So the key would be to get rid of the heat on the other side of that board, right? Okay, anyway, I got carried away a little bit. The other way for the inhibitors is to slow the oxidation reaction by attaching species to the surface. And here is what's called sacrificial protection. We take a material that is more anodic, so it's called anodic protection. And galvanized steel, if you get out and walk towards the library, they have construction, and right next to that construction there's a fence. I want you to look at that fence, because that fence is coated with zinc, and you can see huge grains with your naked eye. You don't need a microscope for that. Question is, why is that fence galvanized? Yes? It's like a scratch. Mhm. Zinc would corrode first. Now eventually once that coating is gone, it's gone and the fence is going to be rusting. So I want you, on the way to another class, to take a look at that fence. And first of all, observe the structure of zinc grains on that fence and see if you can find any rust and where you find it. And next time maybe tell us where you find the rust. For the civil engineers, the sacrificial anode, primarily magnesium, can be connected to the rebar, or in this case it's steel pipe. Like this is underground. Whenever you do corrosion protection for the structure, you have to be careful because this magnesium anode is expandable. You're going to use this material up. So you would need to make the calculation of how long it's going to take for this thing to get dissolved, and once this is dissolved, there's going to be a hole in your structure. Okay, in summary, metallic corrosion involves electrochemical reactions where electrons are given up by the metals in an oxidation reaction. So electrons on the outer shells of metals are taken, and those electrons are consumed in the reduction reaction. So there are two reactions, oxidation and reduction. And all the metals are ranked according to their corrosiveness in standard or in galvanic series. Temperature and the solution composition affect corrosion. It's very hard sometimes to do simulated tests for corrosion because they may not simulate the actual environment that the part is in. Like if you have a metal pipe in the river, those are different conditions than if you take that metal pipe and stick it into the glass of the solution, because there's constant removal of the species, different boundary conditions. And the corrosion can be predicted or prevented by material selection, by dropping the temperature, by having physical barriers, by using inhibitors, or by cathodic protection, where you use a material that's going to corrode before the actual material that you're interested in. Any questions? You can see the word corrosion is 37 times. The first grant that I had was from the Corrosion Society, American Corrosion Society. And as part of that grant, you are required to go to a national meeting, which I think that meeting was in Houston. Every year, maybe even twice a year, there's a meeting with 6,000 attendees. And I used to go to Materials Research Society meetings, which have roughly like 2,000 people. Here, there were companies like Haynes Alloys that would bring in the whole car that's made out of titanium. That was pretty cool. And then, just before leaving, I popped my head into the symposium of offshore drilling. And Mitchell and Clayton wrote this word, and they were with this paper, and they were presenting it. It's called A Critical Review of Current Performance Tests for Offshore Anti-Corrosive Coatings. And The thing is that once this offshore drilling involves a floating house, you get very complicated piece of machinery. So the only way to deliver anything to that is by a helicopter or by boat. So it's not like there's a road that you can put things in. And what they have done is there were 10 manufacturers of protective coatings. And they have done what's called a scratch test. They have taken a piece of metal and they coated it with the coating, and they took a diamond scribe and they made an X and they placed that into the corrosive environment. And after a certain time they took them out, and all of those 10 coatings were rated in terms of their corrosion from 1 to 10. And at the same time, somehow they decided, before putting it into the corrosive environment, to put it first in the liquid nitrogen. And once they did that and placed it from the liquid nitrogen to the corrosion environment, the rating of those coatings changed. So the coatings that were passing started to fail, and vice versa. And because I had prior knowledge, I told him, I said, I know why. I know why those coatings have different ratings. They said, great, why don't you write a paper about it? And the way it works with NACE, the registration was $900. The grant was only, I think, $20,000 for the first year and $20,000 for another. So I just couldn't justify in my head paying like $1,000 for the registration fee. So I wrote this paper. And what happens is the mechanics of the freeze is relatively simple. Whenever you have two materials that have different thermal expansion coefficient, and you heat them up or you cool, one is going to expand more than the other. So they do this. A bimetallic switch, which is in any circuit breaker, works like that. If there's too much current flowing, that current is going to heat up the material. Once it heats up, it bends mechanically and it breaks the circuit. Okay? In case of a thin film, it's very different because the coating is very thin and the substrate is thick, but this thin coating can actually warp the substrate. But here's the equation that relates the thermal stress. This is the elastic modulus times the difference in the thermal expansion coefficient times delta T. Okay? And the larger this thermal expansion coefficient, the larger the delta T, the larger the stress. The stress is always going to be there. Now, when we talked about fracture, this is the stress of the crack tip versus the externally applied stress. It scales as the square root of A over raw. A is the crack length, and raw is the tip radius. So whenever you have a crack, okay, in this case, this is the tip radius, and this is the crack length. So I can tear it up like this, and then all of a sudden it's going to be much easier for me to continue this process. Right? I can continue like this, it's very easy. But if there's no flaw, I can try to do that. See how much force it requires for me to do that? Much higher. So this stress concentration is determined by this equation. Typically the crack length is very long and the tip radius is small. So you have a large number divided by the small number. And then what I did is I just took this two equations and I combined them. Okay? And that explains that during that freeze step, this layer of coating can delaminate. And once it delaminates, it's different than just having a scratch. And I gave two examples of this here in this paper, which was some sign in Krakow that deteriorated over time. This is copper with some plastic, and this is aluminum with some plastic. You can see fracture in the stress concentration points and due to ratcheting, buckling of the same film, and then deterioration due to the corrosion attack. The coating can fail in two modes. One is when there's through thickness cracks like this, You realize this is just a sign on a door, on a glass door in Florida that gets heated up during the summer and cooled down during the winter. Or it could be accompanied by delamination. So this is the paint that has through thickness cracks similar to this, but also delamination. You see, flaking off. So these are the two modes of fracture. And $900. I've saved money by not paying the registration fee because of the published paper. They sell my paper. I don't know how much money they make selling it. I don't make any money from that. Because the experiment was done like over 10 years before the actual paper was published. And there was a Chinese professor who went to Canada, to Alberta, and did this research. And what they observed is that the crack in stainless steel single crystal did not propagate continuously. You see what happened? It was a discontinuous crack, so they could not understand it. Why this crack was discontinuous. Like this. And we were able to explain that using some sort of a model. And corrosion is a big research field. And before we continue with the next topic, I want to show you this paper, which I think I have shown you before, but just to make sure. Vlad Yakubov was an undergrad student here at USF, and I had a grant from the National Science Foundation to bring USF students to China to conduct research. Those were the days where it was very interesting. But this is duplex stainless steel, which has two phases, alpha and gamma. And when you look at the corrosion, you can see that the corrosion attack starts here at the grain boundaries of the gamma phase, and then this is scanning calcium probe microscopy. So it shows the current at the grain boundaries, and these are the peaks in the current, and this is the scale. And basically this one picture explains why the corrosion attack starts at the grain boundaries. There was another paper where we actually measured IV curves. IV means current voltage, and there were three types of behaviors that were observed: a metal, a semiconductor, and an insulator. So with that, welcome to Chapter 18, Electrical Properties. We're going to figure out how the electrical conductivity and resistivity is characterized, or conductance and resistance. Sometimes one word can expose you. And sometimes I see this in student reports. You know what's number one thing? Is when you write down some quantity and then you use too many points past the decimal point. And they actually, I think, teach you explicitly in the classes. Like, when you go buy gas, how much is gas today?
$4.29.
Pump?
$4.29.
$4 and
29.
25-30 cents, but it's actually $4.29.9. Have you seen that? Is that 0.9 cents significant? You realize that if it's less than a cent, it's rounded to the next cent, and you're paying that? Now, at the same time, if you get 10 gallons, that 0.9 is going to become, or whatever, 1 cent eventually, right? So my question to you, for the price of gas, is that fraction of a cent significant? How much do you expect to make when you graduate? What's a good starting salary for a fresh out bachelor's in engineering these days? How much? I mean, it depends where you live, but roughly 70, 80. Okay, does everybody agree? Is that what's the going rate is roughly? My starting salary, do you know what my starting salary at Motorola was? You want to know? How much do you think they offered me? 50 with a PhD. Okay, in the year 2000 in Phoenix. So I had an offer for a postdoc at Harvard for $35,000. And I had an offer from Motorola in Phoenix for twice that, $70,000. And you know what my thinking process was? My thinking process was that I need to negotiate with them. So I said I want 75. And they gave me 72. So that was my starting salary. Because $2,000 didn't matter to the company. And actually, $2,000 added to your salary doesn't make that much, because after you pay taxes, it's not that much. You know what I mean? But somehow I thought that is important. So that's how student writes a report and writes that the thickness of the layer was 11.1655 millimeters. And your accuracy of the measurement doesn't go to that level. So please, when you write down the quantities, you need to make sure that they're significant and they're meaningful. Okay? Conductance versus conductivity, and resistance versus resistivity. What are the physical properties that are phenomena that distinguish conductors, semiconductors, and insulators? And specifically for metals, how is that affected by imperfections, defects, temperature, and deformation? And more importantly, for semiconductors, how it is affected by impurities and also temperature. What is a insulator? You can stick an insulator into the outlet and not get electrocuted. These are the elements of the IC, which stands for the integrated circuit. This is an integrated circuit right here. And wow, look at that. Before copper, the interconnect system was aluminum. And the same thing for the wiring in the house. If you have your grandma's house, it's very likely that it had aluminum wiring. So here we see silicon and aluminum. And there's a process called EDS mapping, energy dispersive spectra. because each material has a certain energy associated with it, and when the electron beam is rastered like this very fast, you can collect the X-rays, and that X-ray signal would give you the specifics. So what you see here are the light regions, that's the silicon region, and you can see here the light regions are the aluminum. So we do have characterization techniques. That's how it looks like under the microscope. And this is a 0.5 millimeter scale bar. It took the industry over 10 years to replace aluminum with copper. And there were a lot of technological issues associated with that. IBM was the first company to introduce copper. The reason you're carrying a smartphone in your pocket is because the whole industry switched from aluminum to copper interconnects. When I joined APRDL in Texas, in Austin, a company called Applied Materials supplied 4 tools to Motorola for inline inspections. And the inline inspections is something that can cause lower yield. And lower yield means that this processor that normally costs $500 is sold for $200 or even $100 when you lower down the frequency. When I started, I put in the wafer like this into the machine. And the machine has a robotic arm. In the beginning of 2000s, there was a startup from Israel that created a tool called Excite. And the manager that worked at Infineon, he was from Scotland. He was very Scottish, so his accent was very hard to understand. Really. I cannot reproduce, but maybe you heard a Scottish accent. He worked at Infineon before, and Infineon used to make memory for computers. And for memory, in the beginning of 2000s, the interconnect system was aluminum. And the aluminum is less shiny than copper, you know? This is interesting because, you see, it reflects the light. Aluminum reflects the light less. So the way it worked, it was like a record player. The wafer would be taken by the robotic arm and placed into the machine from the cassette. There's a cassette of 25 wafers at a time. That's called a lot. Lot. It's the word lot. Then there's a laser that shines the light at this device wafer, and there are a whole bunch of fiber optic sensors that take the light that's reflected from this wafer into the detectors. They had a technician working on this project for 6 months. Now, the advantage of this technician was that he was also from Phoenix area. He was relocated to Texas. The difference was that he was paid like a whooping per diem of like $200 a day. So money-wise, it was a good deal. I didn't get that same deal because, over time, they paid for my apartment and the rental. But anyway, so the first thing I did is I did the test. And you can see this wafer has fingerprints, okay? And over time, these fingerprints turned tarnished because of the reaction, chemical reaction of the oil and moisture from the hands with the copper material. It was a reject wafer like this. And after I put this wafer, I got 23 defects. Then I took this wafer out, and I wrote my name on it, Alex. And I've taken the glove, and I put several fingerprints on it. And I put it back into this machine. And how many defects did I get, do you think? 25? So from 23 it went to 25 with all the fingerprints and my name written on it. So something was wrong. It took a little bit to figure out what was going on. But if you've ever seen the black and white TV, have you ever seen a black and white TV? Or have you ever seen an old analog TV? There were two controls on that TV. One is called the brightness, and the other one is called contrast. And you may want to try this at home. I mean, I cannot guarantee that in your smart TV it would actually work, but if you take the contrast and the brightness and you put them on the maximum, you're not going to be able to see anything. How many of you have ever done digital photography? Okay, you had a professional camera? Okay, if you take pictures on the outside on a sunny day, what do you normally do? You adjust the saturation so it is lower. Because if you have an image that's way too bright, there's nothing you can do. When the image is undersaturated, you can expand it, and you're going to actually going to get details. So what happens in most of the digital photography these days, if you're shooting it and the image is overexposed, you're losing the details in the bright region. So when you're looking for the sky, it doesn't look blue, it looks white. That's exactly what was happening with this device. Because copper is more reflective than aluminum. And then interesting things happen. Have you heard about conflict of interest, and nepotism, things like that? American companies follow certain ethical protocols. In other words, you cannot accept a gift from students, or applied materials in that case. They couldn't pay for your lunch because, you know why? Because you become biased. Okay, they're buying me lunch every day. I'm going to give them a break on a $1 million Excite tool. So they said, Alex, what do you want? You like playing golf? I said, never played golf. Why don't you learn? How about you go to Israel to work with the startup that we acquired to work on this problem? And it's interesting that the computers that were coming from with the tool actually had viruses on them and infected the Motorola network. So I had to cure those viruses back in the day. But the company said, we're paying Alex to work for us. You are our supplier. We're the consumer. We're not here to support our employee to go to a foreign country to develop whatever thing. So that didn't happen. Okay. Have you heard about the Ohm's law? I learned it when I was 12 by measuring the current in the outlet with a multimeter that did poof, I told you about. But V, which is the voltage, is equal to I, which is the current, times R, which is the resistance. And this is actually the voltage drop, J over C. And I is the current in coulombs per second. And R is the resistance in ohms. And I don't think anybody have broken this up for you like this, because voltage is in volts, I is a current in amps, and R is the resistance in ohms. And this is the difference between the resistance and resistivity. Different letter, raw. It's a material property that is independent of the sample size and the geometry. So raw is equal to the R, the resistance in ohms, times A, which is the cross-sectional area through which the current is flowing, divided by L, which is the current flow path length. And you can see that by taking the cross-sectional area and the length of your wire, you're basically taking out the geometry out of this equation. That's the difference between the resistance in ohms versus resistivity. And then conductivity is 1 divided by the resistivity. Please remember that and keep in mind. Which one of these samples is going to have higher resistance? The wire that has diameter D and the length to L, or the material that has the diameter 2D and the length L? So we plug this into the formula of 2 rho L over pi d over 2 squared. This is the area, right? And we get 8 times rho L over pi d to the second power, where d is the diameter. And in the second case, it's rho L over pi, the diameter is 2d over 2 squared. And you can see that in this case, the resistivity of this wire that is twice the diameter and twice shorter is 8 times lower. What does this show? Very often, the current flow is made analogous to the flow of water in a pipe. And the larger the pipe, the more water you can put through. And the shorter the pipe, the better it is. Does that make any sense to you? Okay. Most of the things are intuitive if you just put it down to some tests. In this case, a larger diameter pipe, you'll be able to pump more water, and the shorter the distance, the easier it is to transport that water. So, keeping that in mind, we'll continue on Thursday. But I appreciate your feedback. It was really needed.